Hi, good evening. Can you hear me?
Yes, sir.
Yeah, last two sessions audio. This time I have changed the setup once again. I
Okay,
have
sir.
changed the audio input channel. Hopefully this works.
Okay.
Um, so my name is Satyashide. I'm a PhD scholar at IIT Bombay Electrical Engineering Department. I work on machine design, electric machine design for my PhD, and I take this session every. Could you please mute yourself, Muthu?
Yes, sir.
Yeah. So today, this week, it is about the linear regulator, DC linear regulator. So I don't think we have much to discuss this week. Mm, Maybe it will be over for quickly. We will see. So yeah, I will start with doubts from you. First, I will just discuss what was discussed. There's mostly two things, two kind of DC linear regulators, shunt and series types. So and their advantages, improvements, and all. So yeah, doubts from you.
Sir,
Hmm.
sir, actually, I have the doubt in the last. Actually, this is the previous topic doubt. Can I ask it here?
Yes, sure.
Sir, in the last assignment, uh, actually, okay, sir, do you have access to that assignment? Can you see that questions? Question number 4 and 5.
Okay, wait a minute. Last means week 4,
Week 5, sir.
week 5. Okay.
Sir, in that question number 4,
Hmm.
hmm, sir, here the question number 4, a rectifier circuit is protected from an interest current of something steady state.
Hmm. Hmm.
A rectifier is connected in that question, sir. Actually, it is not clear whether uh, because it is a sinusoidal current is given. So our
Okay, we will
rectifier
see.
capacitor filter won't draw a sinusoidal current.
Wait a minute. Let me. No, but capacitor is not there now. They have mentioned that it is connected across a 500 ohm resistive load.
Okay,
So if your rectifier is connected to a resistive load,
okay, sir.
then the output current is like this.
Yeah,
And if the output current is like this, then the input current is pure sine.
yeah. Uh, yes, sir. I think that's yeah. But, sir, actually, the doubt is on fifth question. I think fifth question. Sorry.
Question 5.
Yes, sir. Question 5.
Okay, rectifier circuit provided.
Sir, here again a point 4 amps RMS sinusoidal current is given, but they are also given inrush current. Uh, this seems conflicting, sir.
Oh, okay, that way you are saying. Okay, let me do once. This is a series thermistor of this rectifier is connected from. Okay, so the question is output voltage. See, what I think is they have mentioned sinusoidal current, input current only to make sure that your calculations are easy. Okay, but still, if
Okay.
you want to be technically convinced, just think it this
Okay.
way,
Okay.
that you fire it. There are rectifier blocks that you can buy from the market, which looks like this, and they have pins like this.
Yes.
Okay, such kind of
Yes.
rectifiers you can buy. So this thing you can take as a block, that when the manufacturers are making the rectifier, they
Okay.
do not know how you are going to use it, what kind of load you are going to connect. So
Okay.
what they are doing, and they also don't know whether you are at all going to connect any resistance or not for induction meter. Maybe they are adding this. I'm just saying, not necessarily this
Okay.
can be there. You can take it
Okay, sir.
like that. But the idea is this has been given to make your calculation easy. But yes, if there
Okay.
is no capacitor outside, there will be no inrush current.
Okay. Sir, actually
Hmm.
there is another doubt regarding that interest current limiting using transformer.
Hmm.
Sir, in that, sir said as soon as the switch is closed,
Hmm.
the frequency across the inductor is becoming very high, ideally infinite.
Hmm.
How that will happen, sir? Because
I think we discussed this thing some time back, that whenever there is a sharp change, that means there is a high frequency component. Suppose
okay,
suppose you have a square wave like this. Okay,
okay,
you have a square. You can do this also by yourself in MATLAB or somewhere else. Not necessarily MATLAB, somewhere else also you can do. Say you have a
okay,
square wave like this. Now you do a Fourier series of it. So if you do a Fourier series, what you will get is f theta equal summation over some an. Say if I draw it like this, then some an sine n theta. Okay, you will get something
mhm,
like this, 1 to infinity. Now you can calculate the values of ans, right?
yes, sir.
A1, A3, all this you can calculate. Now what you do is, after you calculate, you try reconstructing this square wave once again. So maybe there is one online graphing calculator called Desmos. You can use it. So it's a free
Okay,
software. So you first give, say, some A1 sine, say
okay,
omega t, you give. So what you get is, you get one, the fundamental you get. Okay. Now then
yes, sir.
you add A1, sorry, A3 sine 3 omega t. So now it adds the third harmonic.
Mm,
Okay.
yes,
If you keep adding, you will see what will
okay,
happen is, gradually after some um components, after you have added some components, the square wave will start appearing, but it will not come very sharp. It will come something like this. Come, say, like this.
yes, sir. Okay, something
Uh,
similar to square wave will appear.
Something like this. It will appear. So the thing is, you see here, uh, why is this? Why are these things appearing? That is because you have not yet added enough number of high frequency components to it.
Yes, sir.
Now, since you have not added enough number of high frequency, this kind of
Okay.
abrupt changes it is not able to realize, because abrupt change means always high frequency component.
Mhm.
Okay,
Okay.
so more and more you keep on adding frequency to it, these edges will start, means these peaks, and they will start reducing, and they will become more and more like a square. Okay, now if you have, say, a sinusoidal supply from the grid, and if you turn on the switch maybe at this point, what the load sees is a voltage like this. So there is a sudden change. So this thing actually introduces a high frequency component to it.
Okay. So, okay. So there is, sir, is there any relation between that initial value theorem, final value theorem, and this?
Mm,
From that limit t equal to 0, f of t dt equal to minus s into infinity s into f
I
of t.
think something can be established, but I do not know right now.
Okay,
Something
sir.
might be established.
Okay. Okay, sir. Okay, sir. We can go ahead, sir. Thank you.
Okay, other doubts? Anything, not necessarily from this week.
So, sir, so just because of this, in a square wave, a high frequency is embedded in it. That's why the inductor acts as open circuit when it is closed.
Yes, so as soon as you turn it on, this kind of abrupt change in this indicates there is a presence of high frequency component in the voltage. Now, if you have high
Okay.
frequency component in the voltage, an inductor will definitely stop that because
Uh,
it is omega L, right?
okay. Yes, sir.
Or in other words, you can say high frequency, this sudden change of voltage will tend to force a sudden change in current, which the inductor will try to stop,
Mm,
kind of
okay.
act as a low pass filter.
Yes.
Question 3 of assignment 2. Last week's assignment, this week's assignment I cannot discuss. Which week's assignment? Current assignment which you are yet to submit? No, you are yet to submit that assignment, right? I cannot discuss it. Let me check. Are you yet to? Oh, is the deadline over? No, not yet. Question 3 you are saying. My goodness. In the circuit current limitings. This is directly discussed in one of the lectures, right? This exact circuit is discussed. The lecture is there, current limiting circuit. There is one lecture on application, I think. There this was present. Or where? No, overcurrent limiting circuits, there is a lecture. Yeah. Other doubts?
Sir,
Yeah.
uh, sir, actually, if this is regarding capacitors,
Hmm.
there are two different types of capacitors, polarized and non-polarized capacitors.
Hmm.
Uh, in the polarized capacitor is with a symbol of top plate to be dashed and the bottom plate is somewhat curved.
That polarized what you were saying is called electrolytic capacitor.
Yes, sir. This symbol represent polarized, right, sir?
You should say electrolytic capacitor.
Electrolytic. Okay.
Have you seen electrolytic capacitors?
No, sir. That cylindrical shape one, I
Yes.
don't know. Okay.
It looks like this,
Okay.
and it has leads. One large lead, one small lead, and
Okay.
on the body there is a sticker, and on the negative lead, on the sticker, just by the negative lead, there is a black mark like this.
Okay.
So from here, you get to understand which one is the negative lead. This is electrolytic, and another one is these are
Sir,
used at low frequency. Okay.
sir, you're not audible.
Hmm? Just a second, I lost network. Can you hear me now? Can you hear me now? Can you hear me?
Yes, sir.
Okay, there was a network issue here suddenly. Just a minute.
Okay.
You can see the screen, right?
Yes, sir.
Okay, so this is electrolytic capacitor. They are used at low frequency. Uh, Maybe say at the output of a buck converter, or all the capacitors that you have studied. I mean, all the capacitors that you have seen in this course. The capacitor filters, output the rectifiers, everything
Yes.
are this kind of capacitors. And other capacitors are there. There are several types. I think ceramic capacitor, film capacitor, uh, other types of which are written by this. They are small in size. They look like this, like this. They are used in high frequency circuits, or maybe at the positions of the circuits which are high frequency. Say gate drivers,
Okay.
like that.
Sir, this polarized one, two parallel plates. The capacitor is drawn on two parallel plates.
This is not polarized. This is unpolarized.
Oh, sorry, sir. Yes, non-polarized.
Hmm.
Sir, in last class we saw two circuits. Uh, a diode bridge with the two capacitors in series.
Two capacitors in series.
Yes, sir. At the output, across the output, uh,
This one.
just before, sir. Before this is also the one.
Hmm.
This one, sir.
Hmm.
Sir, here in this circuit we have this polarized one at the output.
Hmm.
In the next circuit we have a non-polarized capacitor, two capacitors at the output.
Hmm. No,
Sir, will
actually,
that bring,
okay, go ahead, go ahead.
sir? my question is, if I connect this non-polarized capacitor
Hmm.
to to the first circuit, to the before circuit on the previous question, will it bring any difference to the operation of that circuit?
Generally, unpolarized capacitors are not available at very high values.
Okay, sir.
Okay. But in such applications, we need high value of capacitor. Maybe since it is just after the line, maybe we will need some, say, 4700 microfarad, or maybe uh, something like that, maybe 470 microfarad. I don't think these values are available in the film types of capacitors. I don't think so. They are available.
Okay, sir.
So just a
Okay, sir.
second. I
That
will
is what.
just get it confirmed. Just a second.
Okay, sir.
অরূপদা, এই যে ফিল্ম ক্যাপাসিটার গুলো হয় বা সিরামিক ক্যাপাসিটার গুলো হয়, ওইগুলো 4700 470 মাইক্রোফ্যারাডে পাওয়া যায় না? তো পাওয়া যায়?
470 মাইক্রোফ্যারাড। হ্যাঁ, এখন ভোল্টেজ লেভেলটা কত তার উপর ডিপেন্ড করছে। তুই যদি এখন 20-25 ভোল্টের চার্জ পেয়ে যাবি,
আচ্ছা, ওই হাই ভোল্টেজে নাও হতে পারে।
পাওয়া যাবে। হাই
আচ্ছা আচ্ছা।
ভোল্টেজে 100 মাইক্রোফ্যারাড মানে অনেক। 500 ভোল্ট 100 মাইক্রোফ্যারাড আমি ইউজ করি।
হুম।
থিন ফিল্ম ক্যাপাসিটর সেরকম পাওয়া যায়।
আচ্ছা।
কিন্তু অনুমান পাওয়া খুব চাপ, এর থেকে
আচ্ছা।
বেশি না।
And even if you get these ceramic capacitors, I mean these unpolarized capacitors of this much of capacitance value, most
Okay, sir.
probably you will not get it at the voltage level that is required. See, this rectifier is connected to the grid, so
Okay, sir.
you will need something that can block at least 200 volts, since two are in series. So
Okay,
200,
sir.
maybe even more, if say if you have one capacitor at the output of the rectifier, which is the case most of the time, you will need a capacitor which can block at least a 400 volt, 400 450 volt. So you will not get that, and those capacitors are also meant for high frequency applications, so they are not used. Electrolytics are used here.
Okay, the non-polarized are meant for high frequency.
High frequency, like gate drivers, or maybe sometime we uh, sometime what we do is, say if you have a PCB, and on the PCB there is an IC, suppose, say this is the VCC of the IC, and somewhere is their ground pin of the IC. What we do is, very close to the IC on the PCB, we connect a small non-unpolarized capacitor to make sure that if there is a noise in the power supply, this will absorb that,
Okay,
so that the supply to the IC is not interrupted or uh, polluted.
okay. Sir, is there any difference between the charging behavior? That is this polarized one can charge and discharge only one plate, whereas this non-polarized
See,
can.
capacitor, I do not know that well, but what I am telling now is are very loose statements. Okay, they might be to some extent wrong. Uh, these electrolytic capacitors, they are nothing but RLC circuits inside. Okay,
Okay,
this capacitor, if you can draw the equivalent circuit as this.
okay,
Okay, if you open this, you will see it is nothing but a roll of paper. A roll of, if you see from top, nothing but a roll of paper with some kind of dielectric in between. Okay, so
okay. Yes.
the thing is that since these are very low frequency application, meant for low frequency application, this
Okay,
thing does not come into play.
okay, sir.
It does not come into play. So more capacitor behavior wise, especially if you are designing your circuit while writing equation, things do not change.
Yes, sir.
This you can write for both the capacitors.
Okay,
It's only that where we have, why you use what, which capacitor you use where.
okay. Mm. Sir, actually, in both the circuit, in the first circuit,
Hmm.
I think, sir, the voltage is not 2 V m, no, because once this is charged, before the bottom capacitor charges to Vm, this capacitor discharge a bit.
Yes, discharges a bit, but since nothing is mentioned here, capacitor values are not given, we will assume them to be large capacitors. We can assume them to be large capacitors.
Okay.
I think some question they here say this one. We derived it last class, right? That this circuit is essentially this circuit. Um, Here they, since they wanted us to calculate the values, they mentioned this thing specifically, that the time constant is very large, so you can assume that the capacitors hardly discharge.
Yeah, in this question it's okay, sir, but the previous one that's what.
Here, since nothing is mentioned, you can go with that assumption.
Yeah, okay.
Only thing is that in
Because
such
because there is
cases,
also because there is also for this question,
hmm,
I think there is also another option, some 0.707 Vm, uh, which are very close. This 2 Vm and 0.707 Vm
point
are very
seven
close.
zero seven is I think some 1 by root 2 or something.
Yes, sir. So
Yes.
there comes the doubt which
So
option to
this thing
choose.
basically what they did is, so if someone has forgotten to, what to say, if someone mistakenly takes it as RMS or something, so that kind of option they have kept. But 0.707 cannot be approximated as 2 Vm.
Yes, sir. Yeah, it cannot be approximated, but since it is definitely
No,
not 2
but
Vm,
in that case also, uh, unless you have very small capacitors, 0.707 and 2 means, you have to have really small capacitors to get 0.707 out of it, or maybe very large load. Large load means low value of R.
okay,
But since nothing is mentioned, we can always take it as huge capacitors.
let's see. Okay.
In that way, yes, you can say not a very complete question, but such cases it is always safe to mention your assumptions. Especially it is a subjective question, but in case it is an objective one like this, then you can do much. Okay, any more doubt? Okay, I don't think we'll have much to discuss today. It will be over quite fast. All right, look at the first question. The sinusoidal AC source in the figure has a RMS value of 20 by root 2 volts. Considering all possible values of RL, means the load resistance, the minimum value of RS to avoid burnout of the Zener diode is how much? See here also once again, nothing is mentioned about the capacitor, right? So what we can do is we can assume that the capacitor is very large. So if the capacitor is very large, that means that whatever the peak value of this supply voltage, sorry, whatever the peak value of this supply voltage, that is the DC value here. So it is 20 by root 2 RMS, so peak value is 20 volt. That is held stiffly. Okay,
Yes.
so this circuit now burns down to this. RL, RS. Now see the question. Consider all possible values of RL, the minimum values of RS to avoid burnout of the Zener diode. So in such cases, since they have mentioned that consider all possible values of RS, sorry RL, so we have to consider that value of RL which is creating the worst case scenario. That is in which case or in for which value of RL, is it for very large or is it for very small, does the Zener diode has the highest possibility of burnout. So we will do the we'll first identify that situation, then solve the problem for the value of RS. Now the question thing is that it's a 0.25 watt Zener diode. So there is a limit of maximum current. So if I write IZ, its maximum value is 0.25 by 5, which is 0.05 ampere. Okay. Now what will happen is, you see, some current is flowing through the Zener. So if I write it as IS, IZ and IL, then source current is Zener current plus load current. And this voltage is always 5 volt. Now since this voltage is always 5, see nothing is mentioned about the Zener, so we will assume, we can take that the Zener is holding this voltage constant. So if this voltage is always 5 volt, then the current IS, this is a constant, right? IS is constant. So if IL reduces, IZ must increase, right? If IL reduces, IZ must increase. So what is the worst case scenario? The worst case scenario is IL 0. Are you going to say something? Otherwise, please mute. Yeah. So if IL, so this is the worst case scenario, IL 0, which means RL tends to infinity, basically open circuit. So the worst case scenario happens when you remove the load. Now to make sure that the Zener does not burn out even at this condition, we have to make sure that the current flowing through this is less than 0.05 ampere. Now the question says the minimum value of RS. So for the minimum value of RS means this current is exactly 0.05 ampere. So this is 20 volt and this is 5 volt and the current is 0.05 ampere. So what is RS? RS is 15 by this. So this will be 300 ohms. Now if you go to a shop and if you say I want 300 ohms resistance, they will be able to give you. You know this, right? That you cannot buy any value of resistance from the shop. This is known to you?
Yes, sir.
So there are only some given values of resistance which you can buy. So 300 ohms is available. You can get 300 ohms as far as I can recall. But the question is, if you only say 300 ohm, they won't be able to give you the resistance. They will ask you for how much power that you have to mention. So you see, I said that IS is constant. We found out. So what is the power for it? It is 0.05 squared times 300. So 0.75 watt. Again, just like the value of resistance, you cannot get any power rating. What all power ratings will you get for the carbon resistances? You will get quarter watt, half watt, 1 watt, 2 watt. Okay, so these are commercially available: quarter watt, half watt, 1 watt, 2 watt. So probably you have to go for 1 watt. You have to go for 1 watt. You cannot go below this. To be on the safe side, our engineering thumb rule, 2 times safety factor, if you want to keep, you can go for a 2 watt resistance. So you have to go and say I want 300 ohm 2 watt resistor. There is a very less chance that you will find a shop which is willing to sell you one such resistance. They will ask you to buy at least 50 or 100 maybe, or if you lucky you may get one shop. So when you are going to buy a resistance or designing a circuit, the resistances that you calculate, you have to calculate not only their resistance value but also the power rating. For capacitors, C and voltage rating. In this manners they are being sold. Okay, only capacitor value, you won't get a capacitor from the shop. It might even be possible that the shopkeeper will make fun of you. Okay, that you are electrical engineer, don't know this and all. You have to face if you do quite a experience it is. Anyway, all right, any doubts here?
Sir,
Yeah.
sir, this wattage rating basically gives us the information about the maximum RMS current that we can allow it to
Yes,
pass through the
yes,
circuit.
yes.
Okay, sir.
So once you design a circuit, you find out how much resistance you need. Then also you have to find out what is the wattage rating of that resistance that you need. And then you can go to the shop and buy. You have to make sure that whatever value you have. Okay, let me find out. I forgot the series. I memorized this one it once. Only some given values are available. 470, 2.2 and all this. Yeah, so this is it. What you can get is this, all you can get this and their multiplications. Okay, so it is 10. So if you are getting 10 means you will get 1 also. 12 means 1.2 you can get. 15, 18, 22. Oh, I said it wrong. 300 is not available. 27, 33, 39, 47. I am writing this from one website. Okay, I memorized it once but I forgot. 68 I don't know. 82. So these are the values you will get. So if you are getting 47, you will get 47 ohm, you will get 4.7 ohm, you will get 4.7 kilo ohm, you will get 470 ohm, like this. And as far as I can recall, these values hold for capacitors also. Okay, that you will get. Now you see, for this question we have calculated that we need a 300 ohm and 2 watt maybe. Now 300 is not available, so what should we go for? We are somewhere here. We are somewhere here 300, but that we are not getting. So should we go for 27? Should we go for 33?
33, sir.
33. So for this we have to go and buy 330 ohm 2 watt resistor. I have forgot. 333 is available, not 300. These are very practical things when you are going to the market to get your supplies, electronic supplies for your projects. Maybe these things you have to keep in mind. First few days you will be humiliated by the shopkeepers, but you will learn eventually.
Sir, this numbers, does it has any pattern, sir? Is it 10, 12, 15, 18?
Does it have any what?
No, sir. Does it have any pattern? Or
I don't
is
think
there any?
so. Mm, so I can see difference of 3, 3, 4, 5, 6. Never thought about 6, 8. I don't think so.
Okay.
So if in some cases you need some precise value of resistance, what you have to do is you have to make it by series paralleling these things, or maybe you have to use a pot. There are several pots available, 5k pot, 10k pots, depending on what resistance in what range you need. There are sometimes we need things like there is an IC called SG3524 which is used to generate square waves. So there we need a certain RC value so that we can control the frequency and duty ratio. So in such cases what we do is one resistance will control frequency, other resistance will control duty ratio. So in such cases instead of having fixed resistances we give pots so that we can vary and precisely control the duty ratio and the frequencies. Fixed resistance will be of no help there. They will give a fixed ratio, fixed what frequency and duty ratio. You know how the pots look like? The pots look like somewhat like this. I am drawing it very large. It is not this large. I'm drawing it very large. Something like this that look like there is a channel so that you can put your screwdriver and vary the value of resistances. In reality, they are maybe this small, maybe a bit larger, too large, or something like this. It will look like around this size. Okay, we look into this question. If the input voltage ranges from 20 to 30 volt and the Zener breakdown voltage is 5 volt and the Zener dynamic resistance is 20 ohm, find the minimum value of output voltage as indicated in the circuit. So VO, what is the minimum value of the output voltage that we have to find out. Now it's a linear regulator, right? So minimum voltage will come when the input is minimum. So if they are asking to find out the minimum output voltage, we will solve this circuit taking the input to be a constant DC of 20 volt. Okay, so 20 volt, 200 ohm. Zener diode we will draw as its equivalent circuit like this. Okay, so this is 20 ohm. They say this is now 220 and 1k. We have been asked to find out VO. See, this is VO. Right. What we can do? I think the simplest way is node voltage analysis, right? I can write capital V also, DC circuit. So VO minus 20 by 200 plus, this is how much, 5 volt. VO minus 5 by 20 plus VO by 1k equals 0. Can you solve for VO and tell me? Six 6.25. Getting this? Any doubt? No doubt, then we'll move to the next question.
Yes, sir. Getting, sir.
Okay, this circuit is given. The question is, we have to find out VI. See, there is an op-amp here, okay? And this op-amp has a feedback, working as a feedback. So we know that for op-amp, the input impedance is very high, tends to infinity, and output impedance is 0. So what is input impedance? Input impedance is the impedance between these 2 points, between the non-inverting terminal and the inverting terminal. So say if I write it as VA and if I write it as VB, then the, say, the input current I in is VA minus VB, say, by R in. Okay. Now R in tends to infinity, so this thing tends to 0. So what we can say is, in this circuit, VA and VB, they are very close, virtually same. I think you remember this term of virtual ground from your op-amp circuits, summer circuit, subtractor circuit, and all those integrator circuits. So the same thing of virtual ground. So these 2 points VE and VB we can consider at the same potential. This is there because there is a feedback here. Okay. Now this is 15 volt supply, and if you look here, once again you see this is connected to an op-amp, so the current that is being drawn through this branch is negligible. You can say no current is flowing. So, and since this is a large impedance, we can say that this point is essentially at 3 volt. Why? Because the Zener is maintaining a constant 3 volt here. Okay, so what we get is, we get VA is 3 volt. This essentially means VB is also 3 volt. Now you see, how is VB derived here? VB is derived as a potential divider circuit. Look at this loop, right? So VB, we can say 20 by 20 plus 40 VO, that is 2 by 6 1/3 VO. So what is VO? VO is 3 times VB, which is 9 volt. Right. So this is 15 volt, this is 9 volt, so VCE is somewhere around 6 volt. So definitely this transistor is operating some in the active region. That is true for most, as far as I know, for all the linear regulator circuits, this transistor operates at active region. That is why the voltage drop across it is very large. You see, the whole load current from the source is coming through this transistor only. So whatever load current you have, say IL, the power loss in the transistor is IL times 6. More is the current, more is the loss. This is a drawback of linear regulators, as you know. More is the current, more is the loss. This is nothing but a variable resistance.
Sir.
Yeah.
Sir, here since both the inputs of the op amp B and BB are at same potential, uh, the output of the op amp will be low. No, sir.
No, I think you are getting confused with the comparator circuit.
Okay.
This is not a comparator circuit. You have a feedback here. It is not operating at open loop.
So this output PJT is on.
No, it is in active region.
Okay, active region. Okay.
You see this much of voltage drop across it. Is operating somewhere here.
Yeah. Okay.
So this is the VCE. This is IC,
See,
right?
yes.
So depending on your IC is nothing but load current, isn't it? Because there is 60 kilowatt of resistance in this path. So negligible current. You can say whatever IC is, that is the load current. So if there is IC now, let us see what happens if the load increases. If you have some load, if you suddenly reduce the load resistance, that is if you are increasing the load, if you suddenly reduce the load resistance, so the current remains same, instantly it cannot change. So what happens is load voltage reduces. Now what will happen? That will reduce VB, that will increase this voltage, means the base drive. If this increases the base drive, you are now operating at higher IC, so you shift it from here to here, so the current will increase and your voltage will again increase. So in this way it will regulate the output voltage. And it will hold 6 volt of CE, collector to emitter voltage. Okay, clear about this question is clear.
So that current, can you say it again, sir? How the load voltage?
So we are trying to understand how it keeps the voltage constant. Okay, so you had some load in a steady state. Now suddenly you increase the load.
Yeah,
Increasing
okay,
load
sir.
means reducing load resistance.
Yes, sir.
Say the our load current does not change that first. Okay,
Okay,
so
okay.
reducing load resistance
V naught will.
means V naught is reducing, means
Yes.
VB is reducing, means you are
Ah,
getting more base drive. More base drive means
more. It
uh,
will
IC is increasing.
more IC. Okay.
So more IC, it means it will again take the VO to its level. Again VO goes
So,
to that level. Again your VB comes back to its original steady state value.
okay. Okay, okay, sir. You can go to the next question.
So basically, this is the feedback mechanism of the circuit. You remember no, that you had a variable resistance which you need to control. So there should be a feedback. So this is the feedback, and this is the reference. So your reference minus feedback is giving you the error, which is controlling this to keep the output voltage constant.
Sir, in this problem, can we compute this output current, sir? Uh, Current through the collector of the BJT.
Hmm.
Actually, across this 1 kilo ohm, there is a 12 volts of potential. So 12
Hmm.
volt by 1 kilo ohm is
That current is
0.12.
going through the Zener.
Yes, sir. It is going into the Zener. Okay.
Op amp you can virtually say no current,
No current. Okay.
no
All
input
the
current.
all the current. Yes, sir. Sir, is there any way by which we can calculate the current through this BJT collector?
Hmm. Can we do the, okay? I think for that we have to write a KVL here. Let us see if we can write a KVL. So we have 12 volt of drop here. So if I write 12, just a second. So we can say that the current is flowing the other way around. We have a supply here also. No,
Sir, can we say
This is 15 volt. Go ahead, what you were saying.
No, sir. The output branch also we get 12 volts. Current across 20 kilo ohm is 3 volts, 40 kilo ohm is 3 volts, and then across VCC is 6 volts. So we get 12 volts here also at the output branch.
Why
If you
12
have.
volt?
Yes, sir. Voltage across 20 kilo ohm is 3 volts. 40 kilo ohm is also
Mm-hmm.
3 volts. 40 kilo
6
ohm is out.
volt.
Yes, sir. Total 6. 40 kilo ohm is 3 volts, sir. Because output is 6 volts.
No, output is
Uh,
9 volt.
oh, sorry. Okay, sorry, sorry. Okay, sir. Uh, so if we go with this now, we are getting extra voltage here in this part of 3 volts. 15 volts we are getting, sir.
So we have the VCE, right? So to find out the current, what we have to find out is what is the base drive.
Okay.
What is the base current is flowing. If you can find out, then from the characteristic you can find out the current through the
Yeah.
collector transistor.
Yeah. By
One
beta we
way,
can.
see, one way is if you know the load resistance, whatever the load current is, that much is the collector current. That you can safely say.
Okay, sir.
Okay. But from here, how to get the current? No, I don't think I know.
Sir, I think the details of base current is needed. I think.
That is the only thing required. But can we calculate in some way? No, I don't think it can do from
Okay.
here.
Mm.
Okay. Same question. We did such a question sometime back, no? The first question. Rectifier, then
Yeah. Yes, sir. Turns ratio is
capacitor.
higher.
Yes, only thing is that there is a transformer here. So we can find out the value of VI, assuming C1 to be very large. What is VI? So VI is the peak value. So 240 root 2 by the turns ratio. You should get something like 21 volt.
Yes, sir. 21.21.
Okay, let us say 21 volt for now. The Zener breakdown voltage is 10 volt. Maximum power dissipation is 300 milliwatt. So maximum Zener current is 0.3 by 10, 0.03 ampere. So value of R1. So what is the Zener value? Voltage 10. So what is the answer? 21 volt minus 10 volt by 0.03, isn't it? Same what we did.
366. Yes.
What we did here. How much is it?
366.
Sorry.
3.6.
Okay. Anyway, you are not getting 366 again. You have to go through this list and you have to choose 390.
Yes.
Okay. Last question for today. See, these things are okay. What we have to do is V output waveform. Okay. Now, you see, in this case, the op amp is in comparator mode. There is no feedback. So, these things, this thing here and this thing here, these are power supplies to the op amp. So, the op amp is getting a positive power supply VCC, and its negative power supply VEE is grounded. So, what happens is you have a op amp like this. This thing we can connect to VCC. This thing, if the provision is there, we can connect to VEE. Say this can be plus 15, this can be minus 15, like that. But here it is grounded. So the comparator, which gets saturated always, when it gets saturated on the upper side, it will give 15 volt. On the lower side, it will give 0 volt. Okay. So this is understood at least from the power supply and the circuit, that the output of,
Sir,
yeah,
excuse me, sir. Negative side, you said saturated zero
yes, you see it
because
is
it is
grounded.
grounded.
Hmm.
Grounded.
Hmm. So this is not the
Right.
case here, it is 0 volt. So what we can see from here is that it's a comparator circuit and the supply is 15 and VCC and 0. So the output will switch between VCC and 0, no other state. Okay, all right. So this voltage is coming at the inverting terminal, and it is being compared with some voltage. Not very clear from the question, where does this Vref lie. If the Vref lies here, okay, we'll always get a continuous 15 volt or VCC output. Oh no, Vi is given, sorry. This is from VCC to minus VCC, and you have a Zener and a reference, so definitely Vref is less than VCC. Vref is definitely less than VCC, and this is minus VCC, so Vref is somewhere here, say.
At the midway, sir, VCC by 2.
Hmm? No, no,
Is it
not
at
VCC by 2,
positive? Uh,
somewhere here. Now, how should the output look like? So, when the negative terminal is higher, we are at the negative saturation. Now, negative saturation means 0 voltage in this case. So, our output should look like this. Right? Only for this interval, inverting terminal input is more than the non-inverting terminal input. No, am I doing it wrong? Yes,
yeah, correct, correct.
inverting terminal input is more than non-inverting terminal input, so we are getting 0 volt. Otherwise, we are getting the positive saturation. Had it been, say, if we had a supply of VE of minus 15 volt, then it would look like this. It would look like this. It would vary from VCC to minus VCC. Sorry, not minus VCC, VEE. But since we do not have a negative supply to the op amp, so it will clamp to 0. Generally a bit less than VCC, because the output transistors of the op amp are at saturation, so they are VCE set, which maybe if there is a 0.2 volt, that will come in series, so that much of less you will get. Okay, that's all discussion from my side for today. If you have any doubt, we'll try to answer.
So the second waveform,
Mhm.
the on the right, you drawn for minus 15.
Yes, if you have an negative supply also, so if you have plus 15 volt, minus 15 volt supply to the op amp,
Ah,
then
okay.
we will get output
Yeah,
like
that's
this.
okay, sir. Okay.
Sir,
Yeah.
sir, in assignment number 5,
Um, yes.
fifth assignment, that is previous assignment, last week's assignment.
Just a minute. Yes. Which question?
Eighth question, sir.
230 volt 50 hertz power supply and a resistive load of 100 ohm estimate power factor in a full bridge rectify. What happened?
Without any filter, and the peak current through the diode is 5 amperes. Here, the current input current waveform will also be an
Just
sinusoidal
just
wave.
second.
Okay, sir.
230 volt 50 hertz power supply resistive load of 100 watt power factor full bridge rectifier with a filter when the peak current through the diode is 5 ampere. What is happening? If you have a resistive load of 100 watt
Okay.
and without any filter,
Okay.
peak current should be 3.25. Am I missing something?
We have
Okay, let me copy the question here for everyone to see.
when the peak current through the diode, that is the input current.
No, no, first I think I am not able to understand the question properly. Just a minute. 230 volt power supply, resistive load 100 ohm, power factor in a full bridge rectifier without any filter when peak
Yes,
current.
sir.
So is the circuit like this? Let me first be confirm about it.
There is a screen, sir.
Oh, sorry, I forgot to. Just a minute. So it is here. Acha, 100 watt.
So here current flowing through the load is sinusoidal only.
That's what I'm thinking. It should be unity power factor.
Yes, sir. Me too gave the same answer, but it was wrong.
It is showing very low power factor in the answers.
Yes, sir. Yes, sir. Yes, sir.
I think they are trying to imply something. Say if it is 100 watt,
Sir, actually it is the P naught by VRMS into IRMS use to find the power factor.
just a minute,
100,
just a minute, just a minute. 100 watts. So whatever RMS voltage you have here, if this is a pure resistive load, that much RMS voltage you should get here also,
yes, sir.
right? So this should be, so diode peak current should be, sorry, am I doing
Sir,
anything wrong?
we have to take 230 square, or we need to calculate the average that here for calculating the resistance value. 100 equal to
Uh,
230 square by R. Here, that first equation, 100 equal
no,
to,
it should be V squared because it is RMS voltage squared by resistance is the power.
for a diode bridge rectifier, the RMS voltage is, okay, the same value.
Where from is this 5 ampere current coming?
Sir, that is the peak of the sinusoid that is flowing through system.
Now you see the peak voltage here we have here. V output peak, that is 230 root 2.
Yes, 325.
Right, so 325 volt. So
This
if
is
I have a
VM.
peak of 5 ampere, then my R L should be 65. No, it is RMS. No, just a minute. I'm not sure where this current is coming. 230 volt, 15 per sub, still 100 watt.
Sir,
Hmm.
sir, this P naught is given in this problem. So P naught by the total VRMS into IRMS will give the power factor. Output 100
In
watt is
that way, it is matching, right?
yes.
But it looks technically wrong, don't you think?
Yes, sir. But since power is given, yeah, even they are given resistive load also.
So basically, they want you to do this problem like this. You have a current whose peak value is 5. So current RMS is 5 by root 2, right?
Yes,
And voltage RMS is 230
yes, sir.
times power factor PF equals 100.
Mm.
But this cannot happen, right? Or am I doing something wrong?
Yes, sir. It can't happen because they have said it's a
So
resistive load.
first of all, if it is a resistive load, power factor has to be unity.
Mhm.
Even if I consider it is not a resistive load, say I consider it's heavily inductive load, then also see inductor, if even if you have a large or small inductor, the average voltage across the inductor is zero. So whatever output average voltage you have, that comes completely across the resistance.
Mm.
And at steady state, that only dictates the current. No, I do not think these things are 5 ampere current. How can flow?
I think if the word resistive is removed from the question, this can be done.
Some load.
Mm.
But actually, when you remove resistive, this current no longer remains sinusoidal. We discussed last day, remember?
Yes, sir. It has to be at peak. We have to.
Yes, if you have very large resistance, it becomes square. Sorry,
Mm.
large inductance.
Yes.
Somewhere we discuss here. See, this
Mm.
blue one is the current. So there, okay, they have asked power factor, not the displacement power factor. So that will do. Even if you cannot find it separately, displacement distortion, that will still do. So this can work. Okay, anything else? I'm still thinking about it. If we put an inductor here, will it increase the load current? What is the average value of a sine wave?
Sir, are you talking?
No, I'm not. I'm just doing this.
Okay, okay.
So is it making any sense now? Say it can be like this: square wave current of 5 ampere peak. So if that causes 100 ohm 100 watt loss, then resistance should be 4 ohm. Okay. So
Sir, repeat this. Can repeat this once more?
They said diode peak current is 5 ampere. So
Yes.
let us say it is heavily inductive and the output current is constant as at 5 ampere. Okay.
Okay. Okay.
Then the resistance value has to be 4 ohm. So you get 100-watt loss, right? So what you have is your voltage across the load resistance is this constant because the current is constant. Output voltage is this.
The current is not square wave. Square. It's square, no, sir? Input.
Yes, current is square in the at the input. Load it is DC. If the load current is DC, then input current will be square,
Okay. And the current flowing through diode is square current, no? Square wave current.
not square, pulse like this.
A pulse. Yeah, positive. In D1 and D3, the
Hmm.
positive pulse. Okay.
Then
In
what you
this
have is this is the output DC voltage. Sorry, this is the voltage across
out,
resistance. This is the output voltage. So the inductor voltage is like this, shifted down such that the average is 0. So this area equals this area, shifted such that now this thing makes sense. But 5 ampere 4 ohm will give you only 20 volt. Okay, let it be 20 volt, that is across the resistor only. Rest of it is taken care by the inductances. Now it makes sense. Is it clear to you?
sir,
Yeah.
you are saying the 20 volt R is 4 ohm. So,
So the voltage will be 20 volt across it, and the rest will be dropped across inductor. And over a complete cycle, the average.
100 by 5 is voltage. We are taking like that. Load of 100 watt.
Hmm.
We are taking ratio of.
No, but again, the average inductor is 0, na? The average cannot be 20 volt.
Yes, yes.
I think there is something wrong, or I mean, I am doing something wrong. Since the output current and power both are mentioned, some mismatch happened there. So the resistance value is not correct, I think. Whatever you are getting. For this voltage and power, this current will not come, I think. See, it is not matching. We have tried it in so many ways. Okay. Any more question? Next week there will be discussions on non-isolated DC-DC converters. Things will now start getting more interesting, I believe. Okay, if there is no more question, I think I will terminate this session. No point of sitting and waiting.
Okay, sir.
Okay, sir.
Thank you, sir.
Thank you.